Good day, thanks for joining us. I'm Kody with Up To Kode. Today we're going to talk about 10 reasons why you should avoid wood framing and design your house with ICF. Seven of the 10 features we're going to talk about today are directly related to the fact that you can have any design feature you want with an ICF building with no loss of insulation value. The other 3 reasons I added in on top of that, and they're also very important. There's more reasons altogether, but it's just hard to group it all into one video. So with that, number 1 reason, follow me, we're going to look at some outside corner window units. All right, outside corner windows. So as you see here, and we have another video more detailed than this one's going to be, we're going to try to run through this quick. This is an outside corner window, and if we look over here, here's another one. Like I said, 7 of the 10 reasons. We don't lose any insulation value when we have to do a structural component like this. So this is called a cantilevered header up here. And like I said, I'm not going to go crazy into detail, but this window's 7 feet this way to here. With a cantilever beam, this needs to go back another 7 feet and get anchored down if you're talking wood framing. So if this was a wood building, this would be a solid beam tied all the way back, and technically the wood guys couldn't do this because we actually cheat and wrap our header, which is inside the concrete, around the corner. Right? So let's say you have a 7-foot window with wood, you have a 14 foot long beam that has almost no R value or insulation value, right? And you have deflection and everything else. So with concrete, with the ICF, I have the foam on the outside, the concrete core, I add whatever I need for rebar to meet the design elements or the structural loading. I have foam on the inside, so I have continuous insulation, no thermal bridging, I have all the structural strength that I need, and so there's no loss in R value there. Reason number 2, tall walls. I'm not the tallest critter in the world, but you can see this is substantially taller than I am. And with tall walls is we don't lose any insulation value at our floor. Now, technically where we're standing is a false floor because this window that you see in the background is 24 feet tall and goes to the bottom floor or the main floor. But this bad boy starts in the basement. So we have, let's say 10 feet in the basement, including the floor joist system. Now, I won't get into the details, but we stop it there. We have a cold joint. We move to the main floor. We pour another 10 feet. We stop that, which would end us right here. Then we pour another 10 feet. And then we have a 16-foot tall gable. Now, the best thing about it, like I said, we don't lose any insulation value. At the floors, the floor systems hang off the ICF. The floor joint or the wall and the insulation continue up past and through. Because a floor system is always the worst insulated. I don't care if you spray foam it or what you do. Every joist is touching the outside world. It's in contact with the rim ply, therefore it's just transferring through the joist. We don't have that. Plus we have all the strength, like I said. If you need an engineer to give you specs, that's fine. But in this situation, instead of running 10 millimeter rebar verts, we just run 15 mil. And then all of a sudden you have substantially more strength. In carpentry, we learn about balloon framing. And I always love that idea if you're thinking about wood framing, but it's never practical because this system is balloon frame. We can do it in different sections, but at the end of the day, it's still a monolithic tall wall. Whereas with wood, if you wanted to do this, we're gonna get a 40-foot LVL, frame it up 40 feet, and then pre-insulate or pre-vapor barrier that, where your floor is gonna sit, and then install your floor on top of that. It's not practical, right? Even if you're on a 2-story, anything, then you have to go, they don't make lumber that long. So you have to go LVL studs, all the rest, right? So with this system, it's just so much easier, simpler, and like I said, you always have the strength, way more than you ever need. Number 3 is rake walls or gable ends. So as you see, we actually have a cool little system here where that's a short little gable, and then this is raked on the underside, and then obviously raked on the top side. With ICF, like I said, you never lose your insulation value. On big tall wood walls, you need LVLs or structural members that keep it strong and straight. But with these rake walls, once they're poured, these are freestanding walls. I don't need a roof, I don't need to rely on a roof to hold my gable ends up. Whereas wood doesn't matter if it's built out of LVL. You still need the trusses and the sheeting and everything to hold that stable from trying to tip or rack over. The beauty thing about an ICF rake wall is this is an exterior wall all the way up to there. Now, in wood framing, you have to insulate that up to where the top line of your attic insulation is. That attic insulation is going to carry over here. And then if this was wood framing again, you just have to be more detailed with vaults and things like that, because you always have to insulate the gable end wall to the top side of your attic insulation. This example isn't that great, but it does show how easy it is, because now all I have to do is bat these 2 truss spaces, leave a 1 inch for air gap under the sheeting, but my walls are fully insulated. I don't have to worry about it. So I have all the strength that I need, all the insulation that I need. Now what's probably the biggest and the cool feature that we've done in the past is when you're doing wood framing, if you look around here, these are what they call a parallel core truss. So on the flat, it would just be like it could be considered a joist, but because they're on an angle, it's a parallel core truss. They're 24 inches deep. Now, the wood frame guys, if you have a wood frame building, you can't do a parallel cord truss because there's no strength at the top connection to prevent the walls from spreading out. Whereas with ICF, and we've designed houses like this, we have, let's see, an 8 or 9 foot main floor height. We have a 6/12 pitch, parallel cord, because we can anchor the bottoms to the ICF walls. The walls aren't going to spread. Whereas with wood framing, you have to do a scissor truss. So if you have, let's say, a 10/12 on the outside, you have to have a 5/12 on the inside, half of what the outside is. So if you have a 6/12 on the outside, it's a 3/12 on the inside. Well, those look lame because you don't get the cool effect of what your windows are in relation to the outside of the house. See, this window is a perfect parallel with our roof lines. Whereas if you do scissor truss, the outside's a steeper pitch, but your windows, what are raked, are half the pitch, and it doesn't look as good. Reason number 4, lots of corners. We don't lose any insulation value because we don't have lumber built up on the inside corners or outside corners for strength and for drywall backing. We're just continuous insulation around all our corners. Doesn't matter inside, outside. We have the strength. Like I said, I'm going to sound like a broken record. So we have that corner. We have the other corner. Here we have another corner. Then technically we have a T, because if you can see, this wall actually carries through ends, but that's still a corner, right? Same thing here. We have a T, an end wall, another corner. So this house is just littered with corners. If this was wood framing, we'd have a ton of thermal bridging. Every corner you're losing a ton of heat. Reason number 5 is radius or curved walls. We don't have any at this job site, but doesn't matter. Any ICF block can do curved radius walls. They're a beautiful feature if you want a turret or anything like that on top of it. Just an awesome feature. It's very doable with ICF. It's simple. In all their books, like it doesn't matter if it's Nudura or Fox or Logix, they have in their manuals, shows you what radius and how to cut the block to actually make the radius. So that's very doable and it's a cool feature. Reason number 6 is suspended slabs. We don't have an example here on this job site either, but what a suspended slab does and what the design element behind it is a multitude of things. But like in some cities, you can only use up a certain amount of lot size with your house. So on a garage like this, if this was your suspended slab, so think of a parkade, when you have multiple people parking on top of each other, those are suspended slabs. So when you're excavating, you need a foundation below your garage anyway, 4 feet or whatever. Dig an extra 4 feet or 5 feet and put a theater room below your garage. So then this would actually be your suspended slab and it's hollow underneath, and you create more square footage, right? You can have a house that's more modest in size, let's say 1,000 or 1,200 square feet, and if you have a 900 square foot garage, then you have a 1,200 square foot basement with an additional 900 of living space below grade, right? So that could be a theater room or a cold room or anything like that, and it's actually cheap square footage because you're not, like I said, you've already excavated the hole. You need the foundation anyway. You just need a little more height. You're not adding square footage in size or height. You're not adding a second floor for extra space. So it's a great design element. Yeah, utilize that. Think about that. It's actually a fantastic idea. Even a bonus room. You can do, this is a bonus room above us. And if you needed a certain amount of R value, there's a slab system called Fortress, Fortruss, Fortress. It's got the foam beams and the forming system that stays in place, similar to an ICF wall. You pour your slab, now you have the insulation break between a garage and a bonus room. And now with the energy codes getting more strict, you're gonna need the higher R values. So the Fortress system, the slab is a beautiful system for that too. So multiple uses. Reason number 7, you can offset one floor from another, or you can have girder beams that are ICF, any really intense structural element. So in this scenario, if you look up, this is actually over here is our main floor height. So we're 9'1". Our second floor actually starts right here. So it's offset, it's not sitting on top of the first floor, it's actually self-suspending. So when you come around, now because of design and structural elements, we needed this column. So this column transfers down to a massive footing in the basement. And then again, this whole beam, this is technically a 54-inch tall beam from the bottom of the floor joists here to the underside of the windows above is 54 inches, and that's one giant beam that allows us to carry the second floor independently of the first floor. Now, this is a cool feature. It is a little more work, and when we were building it, the customer, the homeowner here was like, why didn't we just throw an I-beam in there? Why didn't we just throw a steel I-beam right here and then just go on top? And that would have been fine, and that's all good. But what happens is, okay, so here you got to think about this. Let's say we have 2 feet of attic insulation in here, 20 inches or 2 feet, and then let's say your I-beam's the same height. This is attic space on this side. This is room temperature on this side. So this is an exterior wall. If this was an I-beam, there's attachment issues. How do you attach your floor into that? And B, how do you stop that cold transfer from transferring from an attic space to an interior conditioned space? So I think, and that's the whole point of these top 7 reasons so far, is any design element is possible without the loss of insulation value. It simplifies the system. We get all the strength we need. And like I said, it's just a little tweaks with the rebar and you can get the strength that is required. If this was an I-beam, I don't know how you'd get these, how you'd actually hang. I guess you could do a top cord hung floor joist like we did here, but it's not as easy. With these hangers, I just slip it into the concrete and pour it, and then I just set my joists. Steel is just so much harder. You're adding another element in there, another material that you have to work around. Maintain with the ICF, and it keeps it simple. Before we move on, I just want to brag and show off some of our handiwork some more. This is the other side of the house, where this again is the second floor, and it comes into the house, sits on this column, and then goes this way, and it spans this whole length right here. And the cool part is that where this starts here, that wall's in line with this wall and goes all the way up. And the beauty part about that is we don't lose any R value whatsoever in any of these wall connections. So reason number 8 is you're afraid of the cost of ICF, or you're afraid of the system, but you still like the efficiency behind it. So then you maintain, or you go with a wood frame assembly and you add extra materials, extra steps, extra labor to try to get more efficient, closer to what an ICF would resemble, but you're still left with an inferior system. Whatever the cost difference between wood and ICF would have been, now you've bridged that, almost made that null and void, and you're still left with a lesser system. So whether you want to add exterior insulation and do siding, or if you want to go higher end and do EFA stucco, which is a great system, a great way of adding R value, it's just still more time and money. I call it polishing a turd. But for example, even if you don't want to add the exterior insulation, but you want to do spray foam, even spray foam alone is bridging the cost difference gap, and it's still not as effective. You still have thermal bridging, and it's just not the same. You have a wall system that can rot. It's not as airtight, even though it is spray foam, so it's just not the same. So if you want to go with wood frame, that's fine. Keep it at that. If you want wood frame plus more efficient, think about going ICF, because then there's no cost difference and it's the ultimate way better system. So that rolls into reason number 9. If you compare, and I have videos on this as well, just separate ones on this topic, but if you compare the cost difference between a wood frame and an ICF, and keep in mind, ICF to the rafters is you still need a foundation, so the only cost difference is exterior walls above your foundation. So that's the only difference in price, because the rest of the house, you still need cabinets in a kitchen, you still need bathroom and laundry and flooring and everything, paint, drywall, that's all the same, doesn't matter. So really, when you can crunch the numbers, it's about a 5% difference. So keep in mind, for a 5% difference, are you okay with 40% more R value? So with a 2x6, if you actually take the effective insulation value of a 2x6 wall, you account for all the framing members, your headers, studs, everything, plus your R20 or R22 bat. You average that out, let's say you get an R17, maybe an R18 if you don't have many windows or many headers, compared to a true effective R24 insulation value of concrete or ICF. That's a 40%. So you have 40% better insulation value. You have 800%, or that's the dramatic way of saying 8 times stronger wall. and also 10 times more airtight. So that airtight rolls into number 10. So reason 10, and we're living proof of this, we're 10 times more airtight than a typical wood frame building. Now, why do I say that? What's the proof behind that? Is we did a house just recently. We knew it was super airtight, but we didn't do any testing till after the customers moved in. And so they moved in, we did the test, blah, blah, blah. And so that's counted in air exchanges per hour. So how much does that building lose in just natural drafting through the walls or the sockets or the floor or the roof, whatever that is? Most houses, even to today, if you build it, today's standard is you lose about 2.5 to 3.5 air exchanges per hour. So that's the total volume of the house lost to just drafts 2.5 to 3.5 times per hour. So on that house, we had 37,000 cubic feet of air, but we only had a 0.23 air exchange. So if you go from a 0.23 air exchange to a 2.5, that's 10 times more airtight. So even if you're looking, well, even wood frame guys in our neighborhood, if they try to achieve, and they get a 1 air exchange per hour, that's a very good day for them. In our situation, we got a 0.23, we weren't even trying. So I have a video that I'm gonna show you why ICF is more airtight, but that's another day. And another one that we did, so from that test, we went to another house that we had built 4 years prior. And I was thinking, okay, well, if this one was a 0.23, I know that other house is pretty darn airtight. It's probably not as good because we've upped our game. But when we tested that one, it was a 0.42. So we still far exceeded passive spec, blew the wood frame guys out of the water. And like I said, you have all the other features I've talked about today. All of those are added in amongst that. So it's just a very simple, effective system.